Alrighty, let's talk about chapter 4, forces. This should be a good one. All right, so let's start with the idea that forces are represented by vectors. When you're drawing a vector, I'm going to start by just drawing a particle. So it's easiest to draw a vector if we start with just a dot representing the thing. That dot could be like the center of mass. So for a human, it would be like my belly button. And then the vector has some kind of force on it. And the force, remember, has a magnitude, that's how long it is, and a direction, which has the arrow, right? So in this case, it would be this long, however long that is the magnitude. And then the direction would be up and to the right. Okay, so forces are represented by vectors, and we can give them labels like F, and it's a vector, so I'm putting a little arrow on it. So it's a vector in the upright direction. Cool. So when we put forces together, most of the time, an object has more than just a single force on it. So let's draw some diagrams. One of the most helpful things that you're going to do is draw what we're going to call a free body diagram. So let's say I'm going to start by drawing out just like my X and Y axes so that I can keep things straight. So there I am, and I'm going to put my particle right there. And I'm going to say this particle represents Mr. Williams on a bike. So I'm riding my bike. And if I'm just sitting there flat, I would say, okay, well, I know that I am being pulled down by the force of gravity. So I would have a downwards direction, and I could call that the force of gravity, or I could also call it weight. All right, so I have a downward force for weight. And then I also know that I'm not sinking into the ground when I'm on my bike. I continue to be right on the surface. And so I would also have a force upwards that has to balance that, because if I just had the force down, then I would be going down. I'd be accelerating into the ground, which is not happening. So going up, I have a force that's kind of like parallel to the ground. The ground is flat in this case. So parallel to the ground is going to be straight up. And we call that the normal force. So that's represented with N, or I also represent it F sub N. Okay, so that's the force normal. Normal means perpendicular. So perpendicular at a right angle to the ground surface. So there's my ground surface. Here's my normal force. It goes straight up. Now, obviously, if my ground surface tilts, if I'm on a hill, now my normal force is still perpendicular, so it's now at an angle. So it's pointing up at an angle, but still at a 90-degree angle to the ground. So let's kind of show something like that where there's a little bit more complexity. So I'm sitting on my bike at a stoplight, right? I'm just holding in place, totally still. Let's say that I am actually being more active on the bike and I am trying to ride somewhere. So I have my X and my Y axes, not very straight X and Y axes, but they'll do. So, and in this case, I'm going to say that I am on a hill. So I'm going to draw a little hill for myself there. And here's my center of mass on the bike. There's my particle. My weight still goes straight down, right? Gravity still pulls me towards the center of the earth. So I would have my weight going straight down like that, and I'll call that weight. My normal force is now going to push me perpendicular to the ground. So the normal force would be at a 90-degree angle here. There it is, kind of. Boom. So that's going to be my normal force because the ground is now still pushing me out, but it's pushing at that 90-degree angle. So if I wasn't pushing on the pedals at all, if I was just like sitting there, I would end up noticing that I have down like this. I have a straight down component and I have an out component. So my acceleration would be this way down the slope, which makes sense. If I'm sitting on a bike and I'm not pushing on it at all, I'm going to end up going downhill. I'll roll downhill. And I would call that the force net, because that's the overall direction of the force, the direction that I would accelerate. But let's assume that I'm actually attempting to go up the hill. So now I'm going to add in the idea that I would be physically trying to push the bike a little bit. So I might have some other forces. I could have a force that is the tires against the road, or actually it would be the road against the tires, because if I'm pushing on my pedals, my tires are going to go around, and then the road is going to push my tires forward. So I might have a force this way, and I'll call that the force of the road. And then if I'm going fast enough, I also might have a force going the other direction, like that. That would be air resistance. I would have some air pushing against my body and slowing me down a little bit. And I could call that drag, which I'll represent with D. So there I have my total piece there. And if I add all of those up together, I've got one up, I've got one coming back down, I've got one backwards, I've got one forwards, and I add them all up, and my total might be 0, right? So my force net is 0, which means I have a constant velocity going up the hill, right? The force of the road pushing up is bigger than the force of the drag going down, but then I've got the slope as well, so I end up with no net force. If I take away the drag, so if I manage to erase that drag and say there's no air resistance, I'm biking on the moon with no air resistance, but I'm going uphill, which is a weird scenario. Now my force net would be going up. All right, now I'm left with some force net going that way. Cool. All right, so let's just introduce a few different types of forces. We've already talked about a few of them. So the first one is weight, which also I abbreviate as the force of gravity, F sub g, because that's the force that gravity is exerting on the object. You can be W. We can also have the normal force. Normal is the F sub n, and that is perpendicular to the surface. So you'll see the skier here on a slope. That is a right angle, meaning it's a 90-degree angle. So the normal force always pushes outwards from the surface that you're standing on. Then we have two forces for friction. First, I have kinetic friction force. So that's F sub k. Kinetic friction means that it's moving. So if something is moving in one direction, the friction force goes opposite the motion. If I push something along a tabletop, so if I push this board along its track that way, the force of friction pushes against the motion. The board is going this way, the force of friction has to go the opposite way, backwards. So that's a kinetic friction force. A static friction force is the force of friction when something's sitting still. So if I'm pushing on this, but I'm not pushing hard enough, there's a static friction force there. The static friction force is going to oppose the direction that the motion would eventually go if you push hard enough. So in this case, I'm pushing this way. The static friction force has to be pushing backwards against me. If I push hard enough, eventually that static friction force will become a kinetic friction force. So the friction forces go against the direction of motion. One friction force due to air resistance is called drag, and that one's really common, so we give it a name. It's drag, and it goes capital D. Then we also have kind of the opposite of drag is the force of thrust. So thrust would be the push due to gas being expelled. This is like in a rocket or an airplane. An airplane shoots air out or gas out the engines, and that it causes a thrust force. And then if I have a rope and I'm pulling on the rope, I have force of tension. And the force of tension goes in both directions, right? If I pull down, then the tension is down, but the rope is also being kind of like pulled and stretched by the point that's holding it at the top. So it's a tension force on the rope. All right. So let's do a little stop and think. All right. So first, two of the three forces exerted on an object are shown. The net force points to the left, directly to the left. Which is the missing force? Two of the three forces, the net force points directly to the left. Oh, okay. So the net force says it points over here. So overall, I have to go a bigger force over here, right? That's my F net. So that means in order to counteract this one, I need to go down a little bit. In order to counteract this one, I need to go over a little bit, and I need to go over quite a lot. So my third force would have to be something in this direction in order to get my net force to go to the left at all. So I'm going to say like my net force doesn't have to be huge like that, but I have to have some kind of component going that way, which means I have to have a component that way and down to counter out F1 and F2. So I got to have this being my direction, and that would be C F3, right? Because it has to go down and to the left in order to counteract the up and in order to counteract the right. Cool. So Newton has 3 laws. We're going to learn about forces, and there are 3 big laws of forces. They're called Newton's first, second, and third law. The first one is inertia. So Newton's first law can also be called the law of inertia. And the law of inertia says an object in motion remains in motion, an object at rest remains at rest if there are no outside forces acting upon it. So if the total net force equals 0, or if the sum of all forces equals 0, so if these conditions are met, the net force, the total overall force, is equal to 0, that means everything balances out, then an object in motion stays in motion, an object at rest stays at rest. Basically, there will be no acceleration on that object. All right, so let's do another little stop and think. A frog is resting on a slope. So since he's resting, right, remaining at rest, given what you learned in figure 412, what can you say about the friction force acting on the frog? Okay, so I know that the friction force opposes motion. In this case, the frog's resting, so there is no motion, but if there was motion, I know that the frog would end up going down this way. So the friction force that opposes motion has to go opposite. The friction force has to go up that way. So there is a friction force because I know the frog's not sliding down the slope, right? Because there's going to be a force of gravity too. There's a weight, and then there'd have to be a normal force out here. And so the force of friction helps stop it from going down the hill. There's a kinetic friction. It's not kinetic because he's not moving, so the kinetic ones are out. There has to be a static friction force, and it has to be directed up the slope to oppose the downslope motion. So that would be C. Cool. Let's do another one. A boy is using a rope to pull a sled to the right. Okay, so let me draw this out. Here's my sled. Here's my boy. Here's a rope. And he's going that way to the right. What are the directions of the tension force and the friction force on the sled, respectively? Okay, so the boy's pulling to the right. So the tension on the rope would be pulled to the right, right, on the box. So rope to box is pulled to the right. Since the box is being pulled to the right and friction opposes motion, the friction has to go the opposite direction. So the friction would be to the left. So it has to be to the right for the tension and to the left for the friction. So that would be B. All right. So let's do another little example showing how to identify forces. So here's an example of forces on a skier, and it's showing how to kind of like draw a diagram before you get to drawing a force diagram. So before you get to a free body diagram with a little particle, you could start with a picture of the object itself. So in this case, it's a skier being pulled up a hill with a tow rope. So this is like an old school ski lift kind of thing. And it identifies, so first identify the object of interest. Here, the object is the skier. Great, so we drew out our little skier. There the skier is. Somebody's good at drawing, wow. Draw a picture of the situation. Check. Right, he's got a rope there, he's got skis, and then there's the land. Draw a closed curve around the object. Okay, so what the object that I'm paying attention to is just the skier and the skier's skis because they're connected to the skier. Locate the points where the objects touch other objects of interest. Okay, so objects that touch would be right here. There's the rope. Right here, there are the skis touching the ground. And then name and label each contact force. All right, so the contact forces, I got tension, the rope being pulled. I've got the weight of the skier. I've got the normal force where it's pushing back up that way. And then I've got kinetic friction because the snow, even though it would be a mild friction, would have some friction pushing the skier backwards. And then name and label long range forces. In this case, weight is the only one because that's force of gravity. So you label the long range force as weight. Cool. So that's how you can do one of those. Let's do another sample. You have just kicked a rock. Why'd you do that? And it's now sliding across the ground about 2 meters in front of you. Which of these forces are acting on the rock? Okay, so I've already kicked it, so my foot is no longer touching the rock. Basically, the situation is the rock is skittering across the ground in front of me. Okay. Which of these forces are acting on the rock? Well, the rock is sliding across the ground. Here it is. So basically, it has a motion on it, right? It's going that way. I'm going to draw my thing around the rock. I have the weight of the rock. I've got the normal force of the rock, and I have a force of kinetic friction, right? Because the rock eventually will slow down ahead of me. The foot is no longer acting. Okay, so gravity acting downwards. Yes, that is a force. The normal force acting upwards. Yes, that is acting on the rock. The force of the kick acting in the direction of motion. No, I'm no longer touching it, so that force of the kick is no longer present. Friction acting opposite the direction of motion. Yes, friction is. And air resistance acting opposite the direction of motion. I forgot about air resistance. I assume no air resistance, but yes, air resistance would also act on the rock because it is in the earth and in the atmosphere. Okay, so all of those forces would be acting. Nice. All right, another factor, another kind of strategy that might be useful is to draw a motion diagram. So a lot of times it's going to be helpful to draw a motion diagram showing what's happening. So in this case, I have a box, I'm pulling it with a rubber band, and I'm maintaining a constant stretch on the rubber band. So it's just like basically the rubber band serves as a string, just pull, 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 pull. And so the box goes from still to moving a little bit, to moving more, to moving more, to moving more. So it's going faster and faster and faster. So I started by drawing out these green arrows, which are my velocity arrows. So velocity, 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 and you can see the velocity is getting greater. Then if I take a difference between these green arrows, so for example, if I take this one and I just kind of compare its length like that and put it up there, right? That was the previous velocity arrow, same length. That leaves me with a gap right there. And that gap would be how much my velocity increased. That change of velocity over the change of time can also be called the acceleration. So that arrow becomes that arrow, right? There is the same length of arrow. And so my acceleration is the difference in my velocities. So now I know that the acceleration is to the right because I saw that my velocity was getting from smaller to bigger, 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 bigger. So now my motion diagram has indicated the acceleration is to the right. That also is going to end up telling me that the net force is going to be to the right in the same scale as the acceleration, right? My net force has to be that way, which makes sense because the hand and the rubber band is pulling that way. Tension of the rubber band. All right, let's introduce Newton's second law. Newton's second law states that acceleration is directly proportional to force and acceleration is inversely proportional to mass. So directly proportional means when one thing gets bigger, the other thing gets bigger. So if the force gets twice as big, then the acceleration would also get twice as big, right? If I put twice the amount of force, the object will accelerate twice as fast. Sounds good. That's called a direct proportionality. Inverse proportionality means when one thing gets bigger, the other thing gets less big. So if the mass gets twice as big, I go from a small rock to a rock that is twice as large, and I put the same force on it, the larger one will have less acceleration because 1 over the mass, 1 over 2, the acceleration would get 1/2 as much. So the bigger the object gets, the less acceleration I end up getting, which makes sense. If I put the same amount of force on 2 separate objects, I have here a pen. It has a low mass. I put a set amount of force on it. It accelerates rather rapidly. Here is a larger object, a stool. I put the same set amount of force on it. It does not accelerate as significantly. Had a little bit of acceleration, but it didn't accelerate super rapidly off screen. So greater mass, less acceleration, greater force, more acceleration. Good. Now I can actually put both of those together into a combined equation. And instead of just doing proportionalities, I could say the acceleration is equal to the net force divided by the mass, or I could rearrange it to F equals ma. You're probably familiar with that one. That is Newton's second law, force equals mass times acceleration. Acceleration is directly proportional to force, inversely proportional to mass. Good. All right, let's do a sample. 2 rubber bands stretched to the standard length cause an object to accelerate at 2 meters per second squared. Suppose another object with twice the mass is pulled by 4 rubber bands stretched to the standard length. What is the acceleration of this second object? Okay. So I had 2 rubber bands, so that is a force of 2, and it caused an acceleration of 2. Another object with twice the mass, so I'm going to write out my equations here, right? So I know I've got A equals F over M. So the first one had 2 rubber bands and accelerated at 2 meters per second. Okay, so the acceleration was 2. So I'm going to draw this one. The acceleration was 2 meters per second squared. It had 2 rubber bands, and then the mass was, I'm going to say 1. So 2 equals 2 over 1. Cool. Now the next object had twice the mass. Okay, so my next object over here, I'm going to still do acceleration equals force over mass, twice the mass, so that one was twice as much, is pulled by 4 rubber bands, okay, over 4 rubber bands, so the force was 4, and the question was, what is my acceleration? Well, 2 over 1 gave me 2, 4 over 2 is the same ratio, so that should also give me 2. I've doubled the mass, but I've also doubled the force, so the acceleration should stay the same. So my answer should be B, 2 meters per second squared. Right? Because I basically did the force went times 2, the mass went times 2, times 2, times 2, cancels each other out, and I'm left with the total regular acceleration. Nice. All right, units for force. Let's see, force is equal, I'll start here. Force is equal to mass times acceleration. Mass has a unit of kilograms. Acceleration has a unit of meters per second squared. When I put them together, I get a total unit of kilograms meters per second squared. It's hard to say kilograms meters per second squared. It's just unwieldy and it would waste a lot of time. So instead, we made up a new unit and we called it a Newton. So forces are measured in newtons and a Newton is equal to a kilogram meter per second squared. Just to give a comparison to like the units that you're more familiar with, remember Newton force is a unit of weight, or weight is a force. So we would work in pounds. 1 pound is equivalent to about 4.45 newtons. So I weigh about 150 pounds, 145 pounds, times 4.5 would put me in the 675 Newton rate, right? So a human might have a weight of 675, 700 newtons. Or obviously humans come in various sizes. I have a daughter who only weighs like 30 pounds. She would obviously be significantly less. And people come like 300 or 400 pounds if you're an offensive lineman. So obviously that number is not precise, but plus or minus double, triple, whatever. Okay, 3 forces act upon an object. In which direction does the object accelerate? Okay, so now I'm going to balance these forces. So I'm going to take, here is my object there, and I've got an object up, an object down. So I know just up versus down. I'm going to do the y-axis first. Down is bigger, right? So if I took this one and I laid it out here, right? Here's my black arrow. There's my black arrow. I'm still left with a net down. And then I have no force to the right, but I do have a force to the left. So my total would be in blue out here, right? Down and to the left. So which one is down and to the left? That appears to be D. Okay. So D, down and to the left, is the direction of the force. And since force is proportional to acceleration, I would see acceleration in that direction as well. All right, so there are a lot of questions that are going to ask you to do a 3-part component. First, it's going to ask you to draw a motion diagram of a situation. Then it's going to ask you to draw a force identification. And then it's going to ask you to do a free body diagram. We've showed you how to do all 3 of those, but just as a reminder, if you have this little rocket car thing, you could start with the motion diagram. It's going faster and faster and faster. So the acceleration would be to the right. Then for your force identification, you circle your object and try to write all the different factors that are playing onto it. So in this case, I've got thrust pushing it from behind. I've got the weight. I've got the normal force. I've probably got some drag. I would think so, unless it says that drag is not a significant issue in this case. And then you draw out your free body diagram. I turn it into a particle. I draw my normal force going up. I draw my weight going down. I draw my thrust force pushing it forwards. And that leaves me with a net force going to the right. And conveniently, my net force going to the right matches my acceleration going to the right. And if I had a drag force here, I think the problem probably doesn't call for it, but my drag force would just be much smaller, so I can still get my acceleration and my net force going to the right. All right, almost there. Let's do a little force diagram comparison. An elevator suspended by a cable is moving upwards and slowing to a stop. Which free body diagram is correct? Okay, so it's moving upwards, but it's slowing down as it's moving upwards. So overall, I need its acceleration to be negative. I need it to be slowing down while going up. So the acceleration in this case has to be that way, right? Thought of another way, I could draw my motion diagram. So I could say, here's my motion diagram. It's going fast, less fast, less fast, not at all fast. And then my acceleration is the difference between those two, which is downwards. Since my acceleration is downwards, I need my net force to be downwards. All right, force net has to be down. So I need the downwards force to be greater than the upwards force. This one The upwards force, tension, is greater than the downwards force. That's no good. This one, they appear to be the same size up and down, so then it wouldn't be slowing down. This one, the downwards force is greater than the upwards force. That would leave me with a total net down, which is good. This one has a force of the elevator and a tension and a weight. I don't really know what the force of the elevator would be, so I don't think that makes sense. And this one just says there is no net force. Well, no net force would be the same as part B, right? Those two cancel each other out, but there are definitely forces. There's the tension force of the elevator cable, and then there's the weight of the elevator. So I would be left with part C, where I have a net downwards force. All right, Newton's third and final, for our purposes, law is the action-reaction law. So the action-reaction law says that every action is going to have an equal but opposite reaction. I prefer to think of this in terms of forces because it's not like every motion has an equal and opposite motion. This is the idea that if you punch the wall, right, the force of your hand on the wall is equal to the force of the wall on your hand. So if you punch a wall, you might hurt the wall, but you also might hurt your hand, which is why I advise do not go around punching walls. Life tip for the day. If I push down on the table pushes back up on me. You're sitting in a chair right now. You are pushing down on the chair, but you're not falling into the earth. The chair is pushing back up on you. Every force has an equal and opposite force. Cool. So that would be phrased as the force of A on B is equal to the force of B on A. And then I put absolute value signs around it because one would be in one direction and the other would be in the other direction. They're pushing each other opposite directions. So one of them is negative, one of them is positive, or the absolute values of each of them are equal. All right, let's do a little sample on that one. A small car is pushing a larger truck that has a dead battery. The mass of the truck is greater than the mass of the car. The car and the truck are moving to the right and are speeding up. Okay, so they're going to the right and they're speeding up. So they're going chook, 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 chook. Okay, there's my motion diagram. The acceleration is in that direction. Which of the following statements is true? The car exerts a force on the truck, but the truck doesn't exert a force on the car. Well, they're touching each other, so any force that the car exerts has to have an equal and opposite force from the truck. Not true. The car exerts a larger force on the truck than the truck exerts on the car, okay? The car exerts the same amount of force on the truck as the truck exerts on the car. The truck exerts a larger force on the car than the car exerts on the truck because it has a larger mass, okay? The truck exerts a force on the car, but the car doesn't exert a force. No, okay, so that one's definitely wrong, right? So we definitely know they both exert a force on each other. Now, it is accelerating to the right. However, we would treat them, because they're touching each other, as like one object. So the car doesn't actually have to exert a larger force on the truck. They're going to exert equal and opposite forces on each other. Where the extra forces is the road is exerting a force on the car's tires that are allowing it to accelerate forwards. But the car versus the truck is every force has an equal and opposite. They are contacting each other. The contact is consistent. So we have an equal and opposite force. That would be C. The car exerts the same amount as the truck exerts on the car. Newton's third law. And that's also true for like contact, for hits. In football, sometimes the offensive player gets hurt when the defensive player tackles him, and sometimes the defensive player gets hurt because there's an equal and opposite force. The fact that the defender initiates the contact doesn't change the amount of force on the defender. Still an equal and opposite. If I hit a baseball or a softball, I'm putting a certain amount of force onto the ball, but the ball is also putting the same amount of force back on my bat. which is why if I hit it real hard, I get a little bit of like recoil. The bat kind of like bounces back. So you got to practice hitting, I assume. I don't know. I don't know how to play baseball or softball, but you guys might. So maybe you could add some insight there. All right, I am clearly going completely off topic and talking about stuff that I don't really know that much about. So chapter 4, you're good to go. We are going to do all of the multiples of 5 questions and problems. Questions, I think, is 1 through 25 multiples of 5. Problems is 1 through, I think, 65 for this chapter. Multiples of 5. Have fun, and we will post a key for it as soon as they are due. Enjoy.